become once we reach circuits of a large enough size, performing the fast Fourier transform becomes the bottleneck. So the idea is, if we can, rather than defining the circuits over a bunch of polynomials, if we instead define it over the hypercube, we can basically use the same architecture as Plonk, but without having to use fast Fourier transforms, which allows us to get quite a lot of speed up. So specifically for the prover, sorry. So the idea is kind of similar. We're going to encode the circuit using a bunch of polynomials, but now we're going to use multilinear polynomials. So if you've read the Plonk paper, you know we need to prove all the gate identities. We need to prove that the wiring identities in the circuit are true, and we need to then do a quotient check, and this can all be applied basically to a multilinear polynomial. So the big difference is in this last step, we don't use an FFT. Instead, we use this sum check protocol. So when Benedikt arrives, I think if he will go over this bit in a bit more detail, basically how we can use the sum check protocol to check the computation trace of the circuit. So that's the basic idea. Now, why is that useful? Well, as I said, by not needing to use these fast Fourier transforms, we can improve the prover time. So we can get linear prover time. And it also allows us to use custom gates of higher degrees. So for example, if you have a very large circuit and you wanted to use a lot of custom gates, when we're using Hyperplonk, it can reduce the prover time. So for smaller circuits, it's not as effective, or we don't see the advantage. So yeah, we can see here, for example, in a roll-up, for example, 50 private transactions, it gives us quite a significant speed up. So when Benedikt arrives, basically, this is the section I'd like to look at in more detail. Does anyone else have any areas of the paper that they wanted to look into?
Maybe we could talk about the different PCSs a bit, because I think that's the kind of the key to the efficiency of the scheme, and like how it compares to univariate Plonk really depends on which PCS we use.
I see Benedikt is here now.
Hey, hello everybody.
Hi.
Yeah, how do you guys want to do this? I'm happy to answer any and all questions. I had some issue. I was trying to draw some things on my iPad, but my iPad decided to be not completely set up, so I'm not sure if I actually have it available. I'll see in a second, but yeah, I'm happy to answer any questions. I have some slides that I can talk about. Yeah, it's really however you guys want to run this.
So I was just saying that the main thing I'm interested in is how really you're replacing the quotient check in Plonk. So how yeah, how you're using the sum check protocol for all of the different modules, basically. Or maybe we won't have time to go through all of them.
Right. Let me see. Maybe there's Zoom does have a whiteboard thingy, right? Can you with the Zoom like does anybody know this? Like you do
I think at the share part, you check, you type, you click the share and then the whiteboard.
Okay. I'm gonna draw with my mouse, so my terrible handwriting is gonna be even harder than usual. But essentially, so the key thing that we need is this zero check. So I have some polynomial f, and I want to say that f of x. Maybe I'll try to just type. So I want to say that f of x is equal to 0 for all x or x in some space h. So for univariate Plonk, we basically show this by doing a quotient check. So, or actually, let me first say, where does this come into? Well, this comes in or we use this in multiple places, but one of the places that you can see this is that you basically design f, or you build a polynomial that checks all of the gate constraints. So, for example, you have something that checks like, well, you design this polynomial that basically for every value x, it checks one of the gate constraints. So, for example, it checks that the addition is done correctly or that the multiplication is done correctly. And this then reduces all the gates being satisfied is equivalent to saying that this polynomial x is 0 on this entire, on some subspace. Okay. So in univariate Plonk, we do this with a quotient check. So how can we do this with this so-called sum check protocol? Well, first of all, we're gonna, x is now not a single variable anymore. It's gonna be multivariate, but that doesn't actually, well, it doesn't matter. But basically what we're gonna do is we're gonna say that for all x, we're going to say that it's now going to be 0 on the specific subspace being the Boolean hypercube. So what is the Boolean hypercube? Well, it's simply for mu variables, it's all the combinations of 0 and 1s. Okay, so there's, if I have mu variables, then the Boolean hypercube has 2 to the mu entries, just all the combinations of 0 and 1. So how do I do this? Well, there's this famous sum check protocol that basically says for some polynomial, let's call it, let's use a different polynomial, g. So for, let's say for all x in b mu, g of x, is equal to some target value, but let's just say 0. So this doesn't, so it's a protocol for proving this, that the sum of all of these values is equal to 0. Well, this is not quite yet what we need, right? The sum of the values being 0 does not mean that all of the values are being 0. Obviously, if all of the values are 0, then the sum is 0, but it could be that you have, I don't know, 3 and minus 3, and they cancel out somehow. So this isn't quite what we need. But what we can do is that we define a different polynomial. We define the polynomial EQ y comma x. And the polynomial is defined such that it's 1 if x equals y, so on the Boolean hypercube. So if x and y are both, they're both vectors, so we say x and y in f to the mu. So it's 1 if x equals y and x comma y. It's bigger here. In E mu. And it's 0 if x not equal to y and x comma y in E mu. Okay, so actually maybe it's instructive to see what this EQ looks like. So EQ y comma x is you can write it as the product of, let's say j equals 1 to mu. So it has it's a product of mu terms, and it's simply 1 minus xj times 1 minus yj plus xj times yj. Okay, so let's look at this in a little bit more detail. So assume all of the xj's and the yj's are 0, 1. This is what it means, I only care about things that are on the Boolean hypercube. So all of my xj and my yj variables are either 0 or 1. And then this term, so what happens? Let's say we have xj is equal to 0 and yj is equal to 1. Well, if xj is equal to 0, then this falls away, right? This is 0. And if yj is equal to 1, then this falls away. So this is equal to 0. So now suddenly this one term, this entire term, because xj is not equal to yj here, is equal to 0, right? Whenever xj is not equal to yj, this entire equation becomes 0. Well, it's the product of mu of these things. And if only one of these terms is 0, well, then the product is 0. So this satisfies the condition. If x is not equal to y, then this product here is always going to be 0. Does that make sense? Yeah. Yeah, if people want to turn on their camera, it's much more enjoyable, to be honest, because then I can see whether people understand it or I have just blank stares.
Yes, I think that's very good one, very clear one. Yeah, but I don't know if other people have questions for that, but I think it's already very good explanation.
Okay. So let's look at the case where xj is equal to y, or x is equal to y. So all the xj's are equal to y. So, well, then they're either 0, in which case this thing is 1, right? Because 1 minus 0 times 1 minus 0 is 1, and this thing falls away. Or they're both 0, or they're both 1, in which case this is 1 and this is 0. And now we have the product of a bunch of 1s, which is still 1. So this satisfies the case that EQ is equal to 1. So this very nice, this very nice EQ equation, this EQ polynomial, which by the way is multilinear, right? It's linear in each of the variables, is going to be our kind of one of the key tricks that is used all over the place in these subject-based protocols. And one of the other nice things is actually that it's very easy. We use this especially in the batching. It's very efficient to compute this polynomial, right? Even though it's a multilinear polynomial, I can evaluate it in mu time. And it turns out that I can actually evaluate it for many points much more efficiently. Like I can evaluate it for, say, all points, or like 2 to the mu points of x. I can evaluate it in, if they have a certain structure, then I can evaluate this entire thing in essentially amortized cost 1. But that's not so important right now. The only important thing is that it exactly is this function. So it's 1 if x equals to y and 0 if x is not equal to y. So how do we now use EQ and our sum check together to get this 0 check, right? This check that f of x is equal to 0 for everything on the Boolean hypercube. Well, we're simply going to say that we're now going to sum over x in b mu of f of x times eq x comma y. Okay, so this is, let's give this a name. This is a function in y. Okay, this is a function in y. Y is still a variable. But we can see that, let's say, so what do we know about this function in y? So let's say, like, we look at h of, some specific point, I don't know, some specific point on the Boolean hypercube. Well, what does this function become? Well, it becomes we can just plug things in. Sum of eq to 0, 0, another parentheses around it, 0, 0, 1, 0, 1, right? Well, okay, now we can look, we know what our eq function is. Eq is only going to be, it's going to be 1 whenever x is equal to this vector, and it's going to be 0 otherwise. So even though this is a sum over, right, it's a sum over 2 to the mu terms. But most of these terms fall away because this eq is 0, right? So
sorry, do you have an extra 0 in that vector?
I'm sure I do.
Yeah.
Whatever.
Sure.
So what is the sum going to be? What does this reduce to?
It's going to be exactly the value of f at that point.
Yeah, so it's going to be f of 0, 0, 1, 0, 1, right? So the claim is, right, and this holds true for any point y in the Boolean hypercube, right? Whenever we're plugging a point y, we get just that evaluation of f. But what we're claiming is, right, like the original claim is this f is 0 at all of these points. So the claim is that this is supposed to be equal to 0, okay? And so what we have is that we know that h of y is equal to 0 for all y in E mu. Okay? Oh, sorry, small y. And this is like f of this top thing implies this bottom thing. This is like, if this holds, then h of y is going to be 0 for all of the y terms in the Boolean hypercube. I see some blank stares. So we see that it's, for a specific y in the Boolean hypercube, it's just the evaluation of f on that point. And the claim is that f is 0 on all the points in the Boolean hypercube. So we know that h is 0 on all the points in the Boolean hypercube. Right? This isn't yet, we aren't yet done, but like this is an important fact. Does that make sense? Or someone ask a question? Any question?
Can we think of h as so h and f agree on the Boolean hypercube, right? So h is like this interpolant of evaluations of f on the hypercube. Is that correct?
Yeah, you can think of that. That is exactly right. It's the so-called multilinear extension of f on the Boolean hypercube. The important difference, what is the difference between, right? It seems like we haven't gotten very far, right? Because we've gotten from a statement of f of x is equal to 0 for all x in the Boolean hypercube to statement h of y is equal to 0 for all y in the Boolean hypercube. So it seems like we reduced one statement and then changed the names of the variables to another statement. But there's a big difference between f and h. So I didn't really talk about what f is, but f can be is a multivariate polynomial, but it can have higher degrees. So for example, if f has a multiplication gate, then it is a degree 2 polynomial. Or if it has other things, it may be a very high degree polynomial in each of the variables, right? Because usually we construct f to be the product of multiple multilinear polynomials. And so F is multivariate, but higher degree in every variable, versus H. Well, let's look at H. Well, we know that what kind of polynomial is H? It's a multilinear polynomial, right? It is linear. It's essentially just this. The only time this y term appears is in the EQ part. And we know that it's linear in each of the yj's, right? There's no yj squared term anywhere to be found. Does that make sense? Right. Okay, so we know now that h of y is equal to 0 for all the points in the Boolean hypercube. And so if we know this, what else do we know about h? Given the fact that it's multilinear or that it and has mere variables. So it's defined on how many different coefficients this, if we write out like the formula of h, right? We can write out the formula of h, right? And how many coefficients does h have?
It should be 2 to the power of mu, right?
Exactly. It should have 2 to the mu power coefficients. And right, like we know, for example, for a degree, a polynomial, a univariate polynomial with k coefficients or d+1 coefficients, like let's say like a univariate polynomial that has at most k coefficients is uniquely defined also by k evaluations, right? I can always go for these polynomials, I can always go from evaluations, like k evaluations define a polynomial, and they define a k-1 degree univariate polynomial, which exactly has k coefficients. So there's this equivalence. And the same thing holds for multilinear polynomials, that if h is mu linear, well, then it's going to be uniquely defined by 2 to the mu evaluations. If I know like this multilinear polynomial has 2 to the mu evaluations, then it uniquely defines the polynomial. Like there's only one univariate, only one multilinear polynomial that has this structure. So now, if I know, right, like I'm saying h is defined uniquely by 2 to the mu evaluations. And here, I just wrote down 2 to the mu evaluations, right? This is 2 to the mu evaluations of h. They just all happen to be 0. So can someone tell me what polynomial h is?
The 0 polynomial.
Right. H is just simply equal to 0.
Otherwise,
it wouldn't, right? Like, otherwise, this doesn't work, right? H of y is not, like, otherwise h wouldn't be multilinear. If it's in fact 0 on all of the, this is like an if and only if. If h is equal to 0, well, then obviously it's 0 on the Boolean hypercube. But if h is multilinear and 0 on the Boolean hypercube, well, then it just has to be the 0 polynomial. There's no other way. And now this made our problem very simple, because now we simply have to check that h is the 0 polynomial, right? So we can just simply, how do we check that h is the 0 polynomial? What's the standard trick that we want to check that a polynomial is 0?
Just evaluate at a random point and check evaluation 0.
Exactly. So the verifier is going to sends a random point. So it's actually a vector in this case, right? Vector t, and then we evaluate h of t. But now we have to go to the back to the actual definition of h. Well, h was defined by the sum check. So now the sum check becomes this form, and this is exactly now the verifier. This is actually right, like for the verifier, this takes too long to evaluate. This would take 2 to the mu to evaluate. So now we can run this beautiful sum check protocol in order to actually check that, right, this is equal to 0. So the prover and verifier now would engage in a sum check in order to show that this sum here, right, where we plugged in this random vector t, is equal to 0. And the reason that this gives us a 0 check, like now walking backwards, is, well, if this is equal to 0, this implies with high probability that h is equal to 0, which implies that h of y is equal to 0 for all the points in the Boolean hypercube, which implies again that f, because h is the multilinear extension on f in the Boolean hypercube, well, this implies that f is 0 everywhere on the Boolean hypercube, which is exactly the original statement that we wanted to prove. Right? I haven't talked about yet how we do this, but like, let's assume that there's a protocol for this. Does that make sense? Okay. So this is how we, yeah.
Can I ask
Oh,
so I was wondering if is the reason that you use sum check sort of a last resort in the absence of, you know, a sort of division check for in the univariate case? I mean, there is something like that called Alon's Nullstellensatz, but is this sort of the main reason why you opted for the sum check protocol?
I mean, I think there's multiple advantages. So, for example, one of the things that is really interesting is that, say, f is defined as like a product. Like, let's say f of x is like f1 of x times f2 of x, right? Like times some, you know, like selector variable plus, I don't know, 1 minus selector of x times f1 of x plus f2 of x. So it turns out that I never actually need to compute f explicitly. I can run the sum check using just the evaluations of f1, f2 as, you know, like I can just run the sum check knowing basically these evaluations, just use some dynamic programming. And what this means is that I don't have to, I mean, yeah, not having to explicitly instantiate f1 times f2 of x is really important, because otherwise f1 times f2 of x might be huge, right? It could have like a quadratic number of variables. You know, this would be, yeah, the prover time would explode. And even if it's univariate, right, then I need FFTs in order to compute f1 times f2 of x. And the whole idea of this paper was to get rid of FFTs. So that is one of the key reasons. The other really nice reason is that if I the quotient polynomial grows with the degree of, you know, my custom gates, right? It grows with the degree of the it's proportional both in the degree of the custom gate, but also in the number of gates. It's essentially like, yeah, it's proportional in the degree of the custom gate times the number of gates. So this sort of limits the usefulness of super high degree custom gates. Because if I make the high degree custom gate too big, well, then I need to commit to the quotient polynomial, and this becomes the bottleneck. So I can use like degree 5 custom gates, but it wouldn't make sense to use like things much beyond that. In sum check, the really interesting thing is that I never have to commit to f of x, right? I never have to commit to a lot of these things. I mean, I have to have a commitment to f1 and f2 available, but I don't have to commit to these things, and I don't have to commit to any sort of quotient polynomial. And we'll see actually that in the sum check protocol, you do send polynomials in each round, and the degree of these polynomials is essentially just the degree of the custom gate. It's not the degree of the custom gate times the number of gates. So, you know, not like, say, like there's 1,000,000 gates, right? It's not like 1,000,000 times the degree of the custom gate. It's just the degree of the custom gate. So you basically, one of the really nice things, and that the things that allows us to have high degree custom gates, is that we don't have to commit to these high degree polynomials anymore. Everything, you know, that depends on the high degree is done in field operations, which we know are much faster usually than having to commit to these large polynomials. So yeah, I wouldn't say that it's, I think that, you know, like if you're trying to do it another way, like essentially you're getting back to kind of the techniques that we use in univariate, like in univariate zero checks, and those techniques exactly have the downsides that we're trying to avoid.
Can I ask another quick question? So that was a really good answer, by the way. There should be, I assume, like some isomorphism between or group isomorphism between the ring of all multilinear polynomials of, you know, certain variables and all max degree univariate polynomials of, you know, exponential size in that. So do you think it would be possible to do univariate interpolation by doing multivariate and then just, you know, mapping everything to x0, say?
So so multilinear polynomials, I think, are more general than univariate polynomials. So if I have a multilinear polynomial, right, like say I have f of x1 ... x mu, right? But like say I have some, you know, I have some, then I can use this to represent a univariate polynomial by simply evaluating it at I think 1x squared x to the 2 to the mu minus 1 probably. Don't quote me on the minus 1.
Yeah.
Right, like this is there's or I don't know, like the like if I take a multilinear polynomial and then basically, or if I want to, you know, write a univariate polynomial of degree 2 to the mu as a multilinear polynomial, I can literally just take the coefficients and map them to a multilinear polynomial, and then I just evaluate it. Instead of evaluating it at x1 through x mu, I evaluated at x squared up to x to the 2 to the mu. So that's sort of so basically multilinear polynomials allow you to express anything that univariate polynomial does. The other way around is a little bit more complicated. And like, for example, we show that, you know, say you have a univariate polynomial commitment scheme. This is like in the appendix of the paper. But say you have a univariate polynomial commitment scheme and you want to turn it into a multivariate polynomial commitment scheme. This is actually possible using like something called, it's a tensor product protocol from the Gemini paper, but it has log rounds, right? Like there's basically a log round interactive, like you need like log rounds in order to turn one of these things into the other. So I'm not sure if there's an equivalence from like going.
But I mean, instead of FFTs, because there should be an equal number of coefficients in both cases. So you know, I'm thinking you have an O of n way of interpolating a polynomial, and then, you know, the goal is you can map the multilinear polynomial to a univariate one.
Yeah, I don't think that's quite possible. Like,
okay.
Or I guess like the. Yeah, I mean, right, like the thing is that the only fast interpolation that we have for multilinear polynomials, like it's only really fast if you interpolate it on like something like the Boolean hypercube, right?
Yeah, but this is what I'm saying. Do that first, and then you have a polynomial, and then you map that to the corresponding univariate polynomial of exponential degree. And then the question is if that mapping can be done in less than O of n log n.
I don't think you can really map these things so well, because it's like, you know, the evaluation point 0, 0, 0, 0, 0, 1, like the Boolean hypercube, they don't really correspond to. Yeah, I mean, I'm not sure if like the. I mean, maybe a mapping there exists, but like I'm not really sure. You know how that would work.
Okay, we can move on.
Yeah, I mean, anyway. Okay. Any more questions? So
Yeah, actually, I have.
yeah.
Yeah. Because you just mentioned that why you want to use some check because want to avoid there is a very high degree polynomial. I'm wondering why you because actually you just explained that, but I didn't get that. Why the degree is a problem? If you have a very high degree polynomial, what will happen? And how many degrees would be regarded as a high degree? It's like need to be 1,000 or million, I don't know, or just a 10 would be high.
Well, so I mean, yeah, like high degree, I guess it depends what I want to do with it, right? Like, but usually like the operations that I have to do in Plonk is I have to run FFTs on these high degree polynomials, which become a benchmark. Well, they scale super linearly in the degree of the polynomial. So they scale like n log n. And this isn't really a problem if you have, you know, like say degree 1,000 polynomials. Especially it's not a problem because other operations dominate. But maybe around like degree 1,000,000 polynomials, this becomes a problem. And then I think especially it becomes a problem, you know, if I want to implement this on really parallel hardware. Like it's possible to implement FFTs and NTTs on really parallel hardware, but I need to keep everything in memory because there's complex memory accesses, and it just makes our life harder and you know, less efficient. And here, you know, things are very streamable and much better optimized for sort of very parallel architecture. We didn't, you know, like we mentioned that we haven't like fully explored that, but you know, this is sort of we weren't the first ones, right? Like really important. We weren't the first people to use SumCheck, right? This is, you know, this goes back to like GKR, you know, proofs from modules, like kind of the first snarks come from this line. You know, one of the things that one of the main research goals here was to take the techniques that exist from the SumCheck world of proof systems and combine them with kind of the Plonkish arithmetization.
Yeah, I agree with your idea, especially considering if like say million degree gates. It's I mean,
the use case really that we're thinking of is something like ZK EVM, where you know potentially we'll have like 1 billion gates or 2 to the 27 gates, right? Like massive circuits. But
yeah. That's a lot. Yeah, exactly. Yeah, that's a lot. And it's even elegant than FFT. So yeah, that's true.
So I could now I don't know, I guess I could talk about the SumCheck protocol. I think James was saying, or there was some other question that you guys had. I forgot what that was. Yeah, just read whatever you guys want. Like.
Daniel, did you have a question with the commitment schemes?
Yeah, not really a specific question, but it's one thing we could go into. I also wanted to ask, like, I wonder if you're familiar with the methods that Justin Drake described about doing univariate Plonk without FFTs, and I wonder how that would compare to this technique.
You mean like in the Gemini paper, or?
I haven't really read Gemini, but I'm not sure if it's in any paper, but there were just some. I think it's very related, like using the idea of breaking up a polynomial into even and odd coefficients without doing interpolation, just doing it sort of the Fry way, and then but like staying in the univariate setting and But
yeah, I mean, like I'm sure a lot of ideas have been around for, but I don't know all of them. There's like, I know that like the Gemini paper, like maybe Justin had some blog post on how to do KZG style stuff without. So for example, like, I mean, I'm not sure, you know, whether all of that, like, you know, one of the difficulties that we had is, you know, for example, making things work with lookup, and you know, all of these, like the permutation check and so on and so forth, where, you know, one of the difficulties in multivariate Plonk is that you basically, so in univariate Plonk, or in univariate, you know, like what univariate Plonk relies a lot on is that, you know, for example, it says like, well, really, you know, we want to, when we check this gate formula, we check like F1 times X times F2 times omega times X. Like, let's just say W times X, right? We do these shifts. And then, I don't know, like, let's say like square times X. You can basically very easily, you know, because the interpolation is always at roots of unities, and you can very easily shift to the next neighbor using, you know, just multiplying by some variable omega, right? So this is very easily done. It's very easy to do this in univariate Plonk. Multivariate Plonk, this isn't quite as clear because our interpolation point is this Boolean hypercube. So the question, you know, one of the things that we struggle with is, how do you step through the Boolean hypercube, right? Like, how do you like jump from one, like what is the next function in the Boolean hypercube? And we essentially, like, one of the key things that we rely on is that you can simulate the Boolean hypercube using a binary extension field, so F2 to the mu, which is, and then you can find a generator in this field and multiply by this generator. Like, I don't really want to go into the details. I think Bingi will talk about this a little bit at the CESC, I don't know how you pronounce it, workshop on Sunday. So if you're attending that, you can learn more about that. But I hadn't really seen anything like that before. But yeah, I don't know.
I can add a little bit to the discussion. By the way, Bulletproof is the first proof system that kind of doesn't use any FFT. So that's already an example. Gemini, I think Gemini kind of is broad. So I think Gemini choose to do that over univariate because that the paper, when they are working on that paper, they are interested that maybe there is also a multivariate version of the Gemini, but later they find that there might be some similarity between univariate and multivariate. That's that they might be equivalent, although I think mapping might not be there. But basically that if you have a construction that is univariate, you might also be able to get one in the multivariate setting, but there will be a lot of the work involved in that. So I would say that I would say when you are comparing with the Gemini and this paper, actually I think univariate and multivariate might be not like the biggest differences.
No, the biggest difference is that Gemini is designed for R1CS. So it doesn't, for example, do custom gates and lookup and all of these things. Also, I think our proof sizes are significantly smaller, but there's a comparison in the paper. But anyway, okay, moving on. Yeah, do you want to talk about, I don't know also how much time we have, but do you want to talk about polynomial commitment schemes, or do you want to talk about the sum check protocol? I can happy to explain the sum check protocol.
I think it would be good if you explained why you used KCG versus, I mean, there is like TensorFly or something like that.
We didn't use KCG. I think this is a misnomer. And what we describe, proof systems are built, like modern proof systems are built in the following way. They have a poly IOP. So modern snarks, a lot of the most modern snarks. So anything from like Plonk, you know, Sonic, Halo 2, you know, all of these things. They consist of two components. They have something called a poly IOP, a polynomial inductive oracle proof, also sometimes called an AHP, and plus a polynomial commitment scheme. And the poly-IFP is a so-called information theoretic protocol. So the prover can, in this protocol, the prover can send oracles to polynomials, right? Which don't exist in the real world, but like, let's just imagine it could send oracles to polynomials. And then the verifier can query these polynomials and efficiently evaluate the oracle, or efficiently verify the proof, given, you know, like basic queries to these oracles. So a query to the oracle means just like the polynomial is then correctly evaluated at a point. If we then want to turn this into a real snark, what we do is we replace all the queries with, or we replace all the polynomial oracles with a polynomial commitment scheme, and we replace all the queries with opening the polynomial commitment scheme. So I think like there's been, you know, I think it's really, really important and helpful to keep these two things apart, because you can essentially take any poly-IFP and combine it with a suitable polynomial commitment scheme. And by suitable, like really it just matters whether, you know, say I have a univariate poly-IFP, then I can combine it with a univariate polynomial commitment scheme, but I can combine it with any univariate polynomial commitment scheme. And if I have a multivariate poly-IFP, then I can combine it with any multivariate polynomial commitment scheme. And the security assumptions and the cryptography that is being used, this does not use any cryptography. This does not use any hashes, does not use, right? Like it's really just the underlying protocol, right? Like the zero check, like all of these checks, right? Never did I talk about commitments here, because this is, you know, just sort of a protocol about polynomials. And then I need to plug in some cryptographic component in order to make this work. And for example, the question, does this have a trusted setup? Only depends on this. The question is, does this require pairings? Only depends on this. Can I use this? So what we did is we implemented it with the specific polynomial commitment scheme, and the numbers that we give in the evaluation are with the KZG-based polynomial commitment scheme, simply because, well, I don't know, to some degree it was easy to implement. It gives us the shortest proofs. But yeah, you can absolutely use, we also described two different polynomial commitment schemes in the paper actually. But like, yeah, you can use it with many different polynomial commitment schemes. You can use it with Bulbrus, you could use it with Dark, you can use it with something Fry-based, you can use it with Dory. Yeah, there's a whole host of polynomial commitment schemes, and you can just use what we described, like Hyperplonk is a poly-IFP, so it can be used with any of them, right? So the two additional, so KZG is one option, which basically has or KZG-based shortest proofs, which basically gives you the shortest possible proof set. But we actually give two more constructions in the paper for polynomial commitment scheme. So we give a Fry-based, we give a transformation, transformation from univariate PC to multi-linear PC, and basically use this to create a Fry-based multi-linear PC. So there was already Virgo, but you know, they go kind of through almost a recursion route in order to create the multilinear polynomial commitment. And using this transformation, which is heavily inspired by Gemini, it gives you a much simpler multilinear polynomial commitment from Fry. The other thing that is really interesting is that there was this paper called Orion at Crypto this year, which uses these linear codes to create polynomial commitment scheme, a multilinear polynomial commitment scheme. And it has the main advantage that it's just ridiculously fast. So I think they can create a proof for like a degree million polynomial in 3 seconds, which I think is the fastest polynomial commitment scheme out there. The downside is the proofs are like I don't know, 3-4 megabytes. Like they're pretty large. So what we did is essentially we defined, or like we present Orion Plus, which is an improvement on Orion, using in fact Hyperplonk itself in the proofs in the construction of the polynomial commitment, and this gets still fast prover, but proof size down to I don't know, I think like 7 kilobytes or something, like, let's say less than 10 kilobytes. It's essentially Orion already relies on recursive proofs, and we show how you can plug in Hyperplonk as the recursive proof system, and this massively reduces the proof size to something less than 10 kilobytes, while still maintaining the fast proving. So yeah, essentially, yeah, you can use this with any polynomial commitment scheme, and it's really just like whatever, whatever you want. And you can give it a new name if you plug in a new polynomial commitment, but I really think this is like doing it misjustice, because yeah, I think we should cleanly separate, like, I think of Plonk also, like, some people think of Plonk as like, the specific thing with the KZG polynomial commitment scheme. I think this is like limiting, right? Like Plonk is a poly IFE, and then you can use it with KZG to get, a concrete snark, or you can use it with something Fry-based, and I guess we call that Plonk 2, or you can use it with bulletproofs, and we call that Halo 2, right? Or the IPA-based polynomial commitment scheme, and we call that Halo 2. So yeah. Any more questions?
I had a question about the transformation. I was just looking at that before the meeting, and yeah, just trying to wrap my head around it, because it looks very much like Fry, and I wonder, is it like Fry in that we're doing this test at a random point beta, but that random point beta, is it drawn from a small multiplicative subgroup like it is in Fry, or is this like the whole field? But besides,
you mean the transformation from multilinear to univariate polynomial?
I mean, in Appendix B, the transformation from univariate to multilinear.
I think you no, it's drawn from the field.
It's like a randomness from the whole field, basically.
Yeah, I mean, it's the multiplicative subgroup of that, but so you exclude 0, but other than that, it's okay. The whole field minus one thing.
Okay. Got it. Yeah, that makes sense. So yeah, just thinking about it, if we plug in Fry as the PCS, then it's almost like we have 2 layers of Fry. I mean, maybe I shouldn't call it Fry, but it just very.
Yeah, I mean, this is like in the end here, right? Our goal was to build a Fry-based multilinear polynomial commitment scheme. Are you saying whether like you can reduce things into one?
Yeah, that's sort of what I was wondering. Yeah.
That's a good question. I don't know. I mean, that's an interesting question of whether I can do something, like this is a very generic transformation. It's very possible that, if you sort of like look at the details, you can get a better, yeah, it would be cool if you can get a better polynomial commitment scheme, like a better multilinear polynomial commitment scheme from Fry. Yeah, that's totally. I mean, I don't know. To be honest, I haven't thought a lot about that, but definitely not impossible.
So something I'm wondering about with regards to that, and it might be off, but I mean, at the end of some check, you essentially need to verify H at some random point of the field, and with KCG, using KCG for that is for that opening proof is okay, but with Fry, where you use some like Merkle commitment, it's difficult to, I mean, how are you going to make sure that that random point is somehow within your like evaluations that you committed to, right? So isn't that a problem that would arise from using that?
I mean, there are univariate, there are univariate polynomial commitment scheme based on Fry. Like, it's not just, I think like Virgo, for example, or Redshift, right? Like, I think they show how to build, like, this is in general, right? Like, even if I build a polynomial commitment scheme from Fry that is, you know, univariate, like even if it's just 1 point, I have to worry about this, but this is sort of a solved problem. I don't like.
Yeah, that's true. You can use like the deep stuff. I think Starkware called that.
Yeah. I mean, like, this is like, there's references in the paper of how to do this. This is like kind of a solved problem. Like, you're right that I can't just use Fry, right? Like, Fry itself is not a polynomial commitment scheme, but I can use Fry-based things. And yeah, sort of if you look in Appendix B and look at the references there, you'll find more details on that.
I guess one last question for me is, do you have any like interesting directions that you look in or look towards with where you want to like take this next, or possible ways to expand on it?
There's always, you know, I don't know, like there's many ways. I'm not gonna, you know, like scooping is a thing in academia. I mean, you know, one of the like most concrete things. So we've implemented this. We're definitely planning on you know, open sourcing it, and you know, I think hooking it up to say like a Halo 2 type front end would be very interesting. There are some open questions regarding, you know, for example, we know how to, like, in Halo 2, we know how to, like, I talked about this a little bit, we know how to do like simple shifts. So shift from X to like the next element in the Boolean hypercube, which is exactly what we need for lookup. But we don't quite know yet what like how to do higher degree shifts. So shift to like the 10th next element. And in Halo 2, this is actually kind of being used, like in the Halo 2 arithmetization. You can access like many rows before or many rows afterwards. And we don't really know yet how to do that efficiently. And our techniques like seem to not like directly extend to that. So that's an interesting open problem. I think, like, honestly, I'm also like really interested in you know, sort of the claim that we made is that this is very helpful for hardware implementations, and we've been talking to hardware people about this. But yeah, I mean, it would be amazing to see, you know, kind of more and more, you know, hardware implementations like GPU, FPGA, ASIC implementations of the scheme, and see, you know, how it actually performs, where the bottlenecks are, and that can also definitely inform, you know, the next research. Cool. I assume this runs for an hour.
Yeah, if there's no more questions. No. Okay, well, thanks very much, Benedikt. Thanks a lot for your time and
Thank you.
helping us with some of our questions.
Sure.
I think, yeah, with the other paper we'll do next week, but yeah, so I guess, yeah, if we have any other questions, we can drop you a line as well.
Sure.
Okay, thank you very
Awesome.
much.
Thank you. Bye.
Thanks.
Thank you very much.